Hi, my name is Ahmed Sirajuddin from Environmental System Research Laboratory at Hokkaido University. I will present enhancement of cooling performance of metal sealing radiant cooling system by a novel panel with a concave and segmented surface. The content of this presentation is introduction and background, novelty of objectives and the method, experimental setup, CFD setup, results and discussion, and finally conclusions. The radiant sealing panel system is one of the radiant heating cooling system where more than half of the heat transferred by radiation. This system has the advantage of low energy consumption and can achieve a high thermal comfort level. But on the other hand, the disadvantage of this system is the high condensation risk caused by using a low panel surface temperature, and also it can't prevent the hot or cold draft from windows. From the literature, we found there are many innovations which proposed to improve the performance of radiant sealing panel system. For example, using the inclined fans, which can increase convection heat flux, and also using a top flat plate with a bottom groove plate, which also has a higher convection and radiation heat transfer coefficient, and then finally using a triangle corrugation shape, which can enhance the cooling capacity and improve the performance. From the literature, we didn't find any research who studies the performance of the curved panel. So the novelty of this study is proposing a new structure of an over radiant sealing panel with a segmented and concave surface. As we can see from this figure, the length of this panel is 1.7 meter and the width is 0.5 meter with a curved segmented with a chord length of 0.1 meter and radius of 0.06 meter. So the main objective of this study is to answer the question: how could the curved shape enhance the performance of RCP compared with the flat surface RCP? The detailed objectives are investigate the effect of L to R ratio on the thermal performance of the proposed sealing panel. Second is comparing the thermal performance of the curved panel with a normal flat panel. And finally, to find the optimum L to R ratio. The methodology applied in this study starts with experimental investigation to study the effect of the operating condition on the thermal performance of the RCP system. The operating condition used in this study is the effect of the fluid inlet temperature and the fluid flow rate. The second step is to using the CFD simulation to validate the experimental result and to study the impact of different L to R ratio. And finally, we compare the thermal performance of the curved shape with the normal flat panel, and we find the optimal L to R ratio. The experimental setup is summarized by this schematic diagram, which shows the room which equipped with a four cylindrical dummies, which represent the internal load. Each one can generate a heat energy of 60 watt per meter square, and the heating power is controlled by voltage regulators. And the lift room is adjusted at a 40 degrees Celsius, which represents the outdoor condition. In this experiment, the indoor temperature, air velocity, and relative humidity are measured and recorded, so we can evaluate the cooling capacity and the thermal comfort level inside this room. This room is cooled down by using four RCP panels connected in series, and the operating condition of the cooling system is controlled by the flow rate and the inlet water temperature. And two different inlet water temperature and three different flow rate are examined. The CFD simulation proposed in this study is summarized in this slide, where the boundary condition used in this study The temperature, the surface panel temperature is adjusted at a constant temperature of 15 degrees Celsius, and different L to R ratio start from 2 and 0.3 with and without void distance. The meshing used in this study, we use a different mesh element from tetrahedral to hexahedral, and inflation layers are applied around the cylindrical body and the radiant ceiling panel surface to capture the heat transfer at the boundary layer around these surfaces. And we're using the surface-to-surface radiation model to simulate the heat transfer from the panel surface to the surrounding surface. Also, we're using the Bosanisk model to simulate the convection, the free convection heat transfer current, which induced in the indoor space. For the experimental result, so we can see from the first figure, which summarized the cooling capacity, which is divided to the radiation heat transfer and the convection heat transfer at different operating conditions. So we can see that the radiation heat transfer is account more than 50% of in all experiments, but we can see that is convection heat transfer is increased by 20% when we increased the inlet temperature from 15 to 18 degrees Celsius at the same flow rate. And if we compare this performance with flat surface and the panel with the inclined fins in the literature, so we can see the curved shape can enhance the convection heat transfer by 60% compared with the flat one, and by 24% compared with the panel with inclined fins. And if we can see from this figure that which indicates the indoor temperature distribution at three different locations, so we can see changing the fluid flow rate has a less significant impact on the indoor temperature distribution, but changing the indoor temperature, the inlet fluid temperature has more significant impact on the indoor temperature distribution. For the CFD simulation, start with validation of the CFD model by comparing with the two experimental results, the present experimental result and the experimental result from the literature. So we can see a good agreement between the CFD simulation and the experimental work, with the error percentage lower than 1.3%. And for comparing a different L to R ratio, so we can see from the bottom figure the comparison of the indoor temperature distribution at different L to R ratio. So we can see if we add the void distance to the L to R ratio of 1.5, so this can decrease the indoor temperature by 0.9 degree Celsius. And if we compare the temperature distribution contour and the volume of the air, which has a temperature lower than 25.5 degrees Celsius, and the BMV, so we can see the L to R ratio of 1.5 with a void has a best performance, where the BMV is shows a lowest value, and also the indoor temperature shows a lowest value. So this can give us a chance to increase the surface panel temperature, and this can decrease the condensation risk and save more energy. Finally, the conclusion from this study, that is the radiant ceiling panel with a curved shape of L to R ratio of 1.5 with a void distance can enhance the heat transfer, the convection heat transfer, and give a chance to increase the surface panel temperature, which can decrease condensation risk and save more energy, and promote the using of radiant ceiling panel to be more environmentally friendly. Thank you so much for your attention, and we are ready to receive any question through these contacts. Thank you so much.